Hi everyone, and welcome to this introductory session on battery module and battery packs production. I'm really happy to have you here today. My name is Vanessa Rueda. I've been working in battery production for a while already, from modules and pack design to testing and deployment in electric vehicles. Today I will guide you through the journey of battery production from the smallest components inside the battery all the way to a complete battery pack that is going to be ready to power an electric vehicles. Now, I know that it might sound a little bit complex and might be also a bit intimidating, these topics, especially if you are new in the field, but do not worry, we are going to take you step by steps so you can take advantage as much as possible of these courses. So let's get started. Before we jump into the details, let me give you a very quick overview of what we will be covering today. Here is our agenda for this session. We will start with an introduction where we will be presenting an overview of the battery systems in electric vehicles, what is inside the battery pack, what are the components that matter the most, and like this we will get to have a good initial understanding of what are the elements inside of a battery. Then we will go to a product overview. We will zoom in into the actual components that make up the battery systems, the cells, the modules, the pack. We will also look at the different types of cells and how all of those are grouped together, as well as how the selections, for instance, of the type of cell will impact the performance and the safety, as well as the methods that we use in the production. And finally, we will walk through the production process. And this is the hands-on part. So we will see how are the batteries really built in the factories, what are the steps that come first, and how do we test and we ensure the quality along the whole production in these factories. So let's begin by looking at where the battery fits into the big picture of an electric vehicle. What you are looking over here is a simplified view of an electric vehicle powertrain. Everything that is highlighted are the parts that are finally composing the battery pack. That basically is going to be the energy tank for our vehicle. Unlike the gas tank that will just hold fuel, the battery pack is an entire system, as you can see, and it is quite complex. It has to store the energy, but also has to manage this energy. It has to stay safe, communicate with the car, and handle wide range of temperatures and driving conditions. So it's a very complex system. What are the key parts inside this layout? So we will go over in detail in each of these parts in the next slide, but here there is a quick revision of this. In the top of the stack we have the battery pack that, as you can see, is a very big enclosure that sits under the vehicle floor in most of the electric vehicles. Inside this battery pack we will have the modules, that are these ones that are over here. Then these modules are filled with the battery cells. There is also, for instance, the battery control unit that is going to be the brain of our battery pack. There is also the safety boxes that includes fuses, wiring harnesses, there is the cooling system, and all of these components are meant to work together to achieve a safe operation of our system. Other components, for instance, like the charging sockets or the charge cables and cooling system, are also helping us to deliver energy to the battery and to charge it properly so it doesn't overheat, for instance. So you can already see that the battery is not just a box that stores energy, but actually it has to be carefully engineered and it has to be protected as part of the vehicle because it plays one of the major roles in the performance, in the range, in the safety, and in the lifespan of our electric vehicle. So let's now zoom in into each of these key parts so you can get also a better sense of what makes up a full battery system. Let's start then with the battery pack itself. This is, as you can see here, is the most visible and as well the largest part in the battery system. At the end, it is the enclosure that will hold everything together. This enclosure holds the cells, the modules, the wiring, the electronics, the cooling systems, and all of those components must to be packed tightly inside the structure that is designed to be strong and to be safe enough. We can think of the battery pack like a suitcase, for instance, but it's not just any suitcase because this one has to be waterproof, shockproof, fire resistance. It has to, for instance, survive thousands of charging cycles. It has to work under very bumpy roads and even occasional crashing and accidents that the vehicles are subject of. So the battery pack, the job of it is not only to hold the energy, but also to protect all the internal components from the things like the vibration, the dust, the water, and the collisions. The battery pack, as you may have seen in the past, or even in this picture, you can see that it is usually mounted underneath the car floor. When we are using that layout, we usually call it the skateboard, and this helps to keep the center of gravity of the vehicle low and also frees up the space in the cabin of the vehicle. So besides of that, there are many automakers that inside the battery pack adjust, for instance, the pack size. They can also adjust the cooling strategy. They can include different safety features depending on whether we are using it for, I don't know, a city car or performance sedan, or if it is, for instance, a truck. All of those requirements drive the design of the battery pack in such a way that is also more than just a container, but it is the key system of the electric vehicles, and also it is one of the most relevant components that we have to design. Now let's open the battery pack and let's look at what is inside of it. So specifically, we have inside of it the battery models. If the battery pack is the suitcase, then the models are like all of these small boxes that we are gonna pack inside of it. Each of these models will contain a group of cells that are arranged in a specific way depending on the design requirements, like how much energy do we need to deliver, or the power the system needs, or the voltage range that it has to comply with. The models helped also to organize and to manage the cells more efficiently, and also by having like these groups of cells, we are making the manufacturing process easier. We are also improving the thermal control of the battery, and as well, these are very useful for servicing and for having a safety strategy for the battery. For example, if one module fails, you don't have to replace the whole pack. That is going to be very expensive, but only one or that failing module has to be replaced. Modules are often made up to, I don't know, everything between 6 and 30 cells, even more, depending on the cell type and also depending on the requirements of the vehicle itself. When we are using cylindrical cells, for instance, we might have dozens or even hundreds of those cells that are tightly packed together in the modules. However, if we are using, for instance, prismatic or pouch cells, the number of cells that are included is usually lower because the cells itself are going to be bigger. So the modules basically will hold the cells, and also they will provide a mechanical support to hold all of the cells in place. On top of that, we will have bus bars, we will have sensors. Sometimes each of these modules will have a local BMS, a local battery management system that is called a slave board, that is going to be in charge of monitoring the voltages and the temperatures inside of the modules. So when you think of a model, you can think that this is going to be the perfect balance between the scale and manageability of the amount of energy that we can have. Is going to be small enough to monitor and to replace it whenever it is needed. And once we group many of those, we have the requested amount of energy to supply a full electric vehicle. Now let's zoom in even further to the real star of the battery show, that is going to be the battery cell. The cell is the basic unit where the actual electromechanical reactions happen, and it is the thing that really stores the energy inside of our bag. It's able to store it, to release it, and to recharge it. In general, we will see later on, and maybe you have seen also, there are these three types of battery cells. We have the cylindrical, the prismatic, and the pouch cells. Depending on the type of cell that we use, the whole design of the battery will change. And each cell will have some advantages or disadvantages. At the end, the cells are going to be super critical because their size, the shape, the chemistry, and the structure, it will determine not only the performance and the range of the vehicle, but also, for instance, it will determine the charging speed, the lifespan of the pack, and how safety it is the battery. So in short, if you get the wrong cell choice, everything else is going to be harder and more expensive, and that is why designing around the cells is the first and the most important decision in the battery pack engineering in general. Now that we know what is actually storing the energy, let's see everything that is around, and let's see how the energy is actually going to be moved, and how the energy is going to be transferred from the battery to the system. This is only possible by means of the wiring harnesses that are across the battery. The wiring harnesses are like the nervous system of our battery pack. So it is going to be the set of cables, the connectors, plugs, and that are going to be across the battery, and that will be allowing the flow of electricity wherever it needs to go. In the battery, we will have two big roles for wiring. On the first side, we have the power wiring, that are all of these thick cables that carry high voltages and high currents from the battery modules to the electric motor and to other systems in our vehicle. But additionally, we also have signal wiring. These are going to be thinner cables that will carry only low voltage signals, for instance, for control, for communication, for monitoring. for example, for sending information of the temperature from the battery sensors to the BMS, the voltages, the CAN communication of the vehicle, and so on. So inside of the module, the wiring harnesses will typically be connected, or the signal harnesses would typically be connected to the voltage sensors, to the temperature sensors, and from there to the local BMS board or the slave BMS board. The harnesses connect also all of these signals to the main BMS and also serve to control the cooling systems, the charging systems, and so on. Then, very closely related to the wiring harnesses, we have the charging socket and the control unit charging. When we need to see how the energy gets into the battery in the first place, we need to talk about the charging socket and the charging control unit. So the charging socket is going to be the plug that we use to connect the car to any energy source, whether it is a slow home charger or it is a fast public charger, or even if we are using supercharger stations. It is not just, this plug is not going to be just as simple as the plug that you use to charge your cell phone. It is going to be way more complex, so it is a very important element in our battery. The electric vehicle charging socket and the system that needs to work with it needs to handle high currents and even sometimes very high voltages, up to 800 volts, for instance, in some modern cars. So it is a critical component of the system. Because of this, the socket and the cable must be very robust, and also because of that, this system usually includes a special feature, for instance, to have temperature sensors that will detect if the battery is overcharging because of too much current. Also locking mechanisms, so the cable cannot be unplugged while charging. Also, it includes communication lines that allows the charger that is outside of the vehicle to communicate with the vehicle, and alongside with the control unit charging to translate the different variables of the vehicle to the external charger, and in such a way to be able to manage, for instance, the speed of the charging, the voltage and the current the labels, and any safety shutdown to be controlled from there. And to go next, there is also a very important element that many people tend to overlook when they hear the word battery. That is actually the cooling. Just like in a laptop or in a smartphone, when you charge it or when you are using it can get hot. An electric vehicle is going to be the same, and the battery of an electric vehicle will also generate heat, especially when we are using fast charging or when we are hard driving. And if that heat builds up too much, it can reduce significantly the battery life, and in some extreme cases it can even lead to safety issues. Because of that, we need a very good cooling strategy, and the cooling systems comes into place. It can be as simple, for instance, as radiators that are key parts of it. In this case, as you can see, as it is highlighted, the radiator will work just like the radiator in a gasoline engines, and it will move the coolant through the system, carrying the heat away of the battery. So in the battery, the coolant usually will circulate through all of these plates and all of these pipes. It will run to the radiator, and then it will be back again into the loop, keeping the battery cool. On top of that, in some cases where their batteries intend to work in very cold weathers, we might also need to include a heater that will bring the battery up to the right operating temperatures before driving or before charging, and this is going to be especially important in places with very harsh winters because the charging at cold weather can damage the cells itself, and it poses a safety risk to our batteries. And we also have the high voltage accumulators, and inside of it we can have the main electrical distribution area when we will include the contactors, the different fuses, the switches of the battery, some pre-charge circuits, some monitoring systems, and all the different components that also allows to keep the battery operating safely. And the last of our components is going to be the battery control unit that is also called the BCU. This is one of the most important parts of the whole system because it's basically the brain of the battery. The BCU is part of the battery management system, or it's part of the BMS, and the job that the BCU does is to make sure that the battery is always operating in a safe, balanced, and efficient way. This communicates with all of the modules and with the slave battery management systems that are in the modules in such a way that it can guarantee that the full pack is operating safely. It also calculates, for instance, the state of charge, the state of health of the battery, and basically it is connected to all of the boards inside of the modules, collects the data locally, process them, and take decisions based on that, managing the contactors of the battery, controlling the charging, discharging limits, and communicating with the rest of the vehicle via CAN or using any other protocols that are available. Great. So up to here, we have gone through all the main components that make up a battery system in an electric vehicle, including the cells, the modules, the pack, the harnesses, cooling system, control units, and so on. Now that we have better understanding of what is inside the battery, let's see how we put all of this together. And in the next part of this session, we will see step by step how to go, how all of these come together, and then how we have the production process. And now then let's go and let's get also a bit more technical, and let's talk about how the cells are gonna be interconnect between each other. How the cells are going to be connected together electrically inside of the battery models, because this is going to be a key aspect of integrating the battery packs. This step is very, very important because it is the way that we use to combine the small voltage and energy of individual cells into a high performance models, and then later on into the packs that we need for the electric vehicles. So when we are talking about the interconnection and when we want to analyze how to connect the batteries, basically we have two main ways to connect the cells. The first one is the connection in series that you can see over here, in which we increase the total voltage of the module. In series, you are connecting the positive terminal of one of the cells to the negative terminal of the next one, and in this way the voltage will add up. So in case we have 10 cells of 3.6 volts and we connect them in series, the module voltage will be in total 36 volts. On the other side, we have the parallel connection, and when we are having a parallel connection, we are basically increasing the amount of energy that the module can store. So when we are doing the connection in parallel, we are going to be connecting the cells positive to positive and then negative to negative. And like this, the capacity of the battery will add up. and it will increase. If we connect 10 cells in parallel, the resulting voltage will be the same. It's going to be 3.6 volts, but the capacity will be increased 10 times. That is the difference between the two interconnections models. In most of the battery models, we use a mix of both serial and parallel connections. Often we use the nomenclature, for instance, 12S2P. That means that we are having 12 cells in series and 2 cells in parallel in each of our models. There are different ways that we can use to have these series and parallel connections, and we also use different cell contacting systems. There is not one standard for all of them, and usually the layout will depend on the type of cells that we are using, the structure, the layout of the module, and also the target cost and the performance that we are using. We can use, for instance, bus bars to have this serial connection. We can also have nickel tabs for doing it, or contacting frames. There are several alternatives for having these connections in the battery cells. All right, so now let's take a deeper look at the components that go into the battery module. That basically will depend on the type of cells and the type of format that we are working with. In this slide, we show a comparison of the bill of materials, or the BOM, of the 3 different module types. First, we have the prismatic cells, then we have the round cells of the cylindricals, and finally we have the pouch cells. Each column in this table will break down the parts that are going to be into each kind of module. As you can see, everything that is common between modules is already highlighted with the yellow boxes, and we can focus then on the things that are going to be different. But let's go first quickly on the things that are going to be similar, or the parts that are going to be into any battery module, regardless of the structure. So first we have the BMS board, the sensors, the insulating layers, the gap pads, the contacting system that we just talked about in the last slide, the high voltage connectors that will connect the modules to the outside world. We may have bus bars to connect the cells in series or in parallel, and we will have also the lid, as well as some mechanical fastening to hold everything together. All of these are common to any battery pack that we use. They are integrated differently, but in general they are the same. But let's talk what is more interesting, that are the things that are actually different between them. So first we have in the prismatic cells, the cells are going to be different for each of those, but we can see that in the prismatic cells, for instance, we need to have the module housing that is going to be different. We have a rigid module housings with plates that are used for holding the cells. Also, in this type of cells, we need to glue together the cells for structural stability, and because of that we have these side plates and pressure plates that keeps everything in our module together. On the side from the cylindrical cells is going to be a little bit different. Usually when we have cylindrical cells, we need to put a cell holder, or that is basically a plastic grid that will hold the rounded cells in place. These modules, because of the structure of the cylindrical cells, it will leave space and some air between cells that can be also used for cooling. The outer casing can be less rigid, since the metallic casing of each of the cells already provides some strength, and also because of that are well known to be the cheapest option between these 3 type of modules. And finally we have the pouch cells. For the pouch cells, we also need a very special module housing. We need also some cell frames or drawers, because each of these cells is very soft and it is very flat, so we need somehow to create mechanical stability for all of them. You will often see springs and or flexible bands around this because they need to apply pressure across the battery cells, as well as the housing must be allow some kind of movement, since the pouch cells can expand and contract slightly during the charging and the discharging cycle. So as you can see, there are small differences between all of those, but at the end the bill of material will affect the weight, the cost, the thermal management needs, how easy it is to assemble and to disassembly the modules and so on, as well as the packaging density and the energy density of the pack will depend on all of this. So the decisions that we take around it will connect to the business goals and to the battery design of our vehicle. This is a better illustration of the three different battery models, and here we can compare more, also see visually how we're actually built and how these modules behave depending on the type of the cells. So let's start with the pouch cell, that is the one that is here at the beginning. So each of these small strips that you see here is representing one pouch cell. As you can see, they are very thin, and also they are very flexible, almost like if you were seeing a big potato chip bag that is going to be filled with energy, since at the end these cells are surrounded by metallic foil that is not rigid but actually is very flexible. One of the most important things with pouch cells is that, as I mentioned, they need to expand and they need to shrink when they are charged and when they are discharged. And this is the natural behavior of the chemistry that is inside. So in order to handle that, each pouch cell is usually placed inside a frame, and multiple of these frames are stacked together. Also, these frames are going to be spring loaded, or they are going to be clamped with some tension elements that will contain the swelling of the battery cells. Cooling for pouch cells is very simple. We can have air convection, and also we can, for instance, have liquid cooling plates behind the battery cells, and in such a way to use that to flow coolant across the different cells. On the other side, we have the cylindrical cells. These cells are hard, they are rigid, so we can compare them, for instance, with soda cans. In a cylindrical module, the cell, as they are already rigid, they are fixed tightly into place using the plastic holder that will not allow them to move in case of vibration and so on. As you see, also there are going to be small gaps between cells, and this can be filled either with coolants, or we can make some airflow or coolings going through this space, and like this to help aid the dissipation of energy. And on the last battery module, we have the prismatic cells. The prismatic cells are at the end like small boxes. They are rigid and they are rectangular, as you can see here, so they can be easily stacked together without having too much gap between them. In this case, the cells are going to be usually glued together with a very thin layer of adhesive. This glue does not stick them together. Besides of sticking together, they can also act as a thermal and electrical insulator. That is also very important for the safety of the full battery pack. So these are like the main difference between them. The choice between pouch, cylindrical, or prismatic. It is not only about what is the cheapest and what has the higher energy, but also it is a whole system decision based on the available space that we have in the vehicle, the cooling strategy, the target cost, the safety requirements, and even to define how easy it's going to be to manufacture and to repair all of this. So if you are designing a battery system, you don't just pick a cell, just pick a cell plus the module strategy and plus the pack strategy that fits overall the performance and that aligns with your business goals. To advance a little bit with the discussion also, and to go a little bit more technical and to know more details of how these battery modules are assembled, let's discuss about something that is also very important, that is how do we keep the batteries stable over time, and why it is important to have the tensioning in our batteries. So when we are using prismatic or pouch cells, we have this phenomenon that I already mentioned, that the batteries will expand or contract a little bit during every charge and discharge cycle. If we don't control the swelling of the battery, at the end this can damage the cells internally, because if they swell too much, the integral mechanical properties of the battery will degrade, and this can cause connection failures, as well as it will reduce the overall life time of our battery. So to prevent that, what we are going to do is, once we have the battery module assembled together and the entire cell stack is inside of the module, we apply some mechanical tension. There are three common ways for doing that. The first one that we have is, for instance, to have this tie rod. That is one of the methods that can be used. Here there are metal rods that run through the module like skewers holding a sandwich together. Also we have the nuts at the end that are tightening and applying a steady compression force, and this method is very simple and it is very cost efficient. The other method that we have is the screws that you can see over here. In this case, the plates are placed at the end of the stack, and the screws are basically pulling the plates together. It is a little bit more robust and allows easier adjustments during assembly and so on. So you can see often many packs having these screws around holding everything together. And the last one that we have here is the steel bands. These are like very strong steel straps, kind of the ones that you see in shipping pallets, that wrap around the whole module and that keep the tensions around it tight and locked in place. The fixing elements, whether they are the rods, the screw, or the band, do not carry any current, and they are only there to apply mechanical pressure. So when the engineers are choosing between this method, the questions are usually to ask what is the cheapest option, what fits the best to the space that we have, what is the best option that we have to assemble in a production line, what is the method that will survive the stress that the vehicle is supposed to handle, and also the lifetime of the battery itself. So there are a lot of things to consider even deciding this simple tensioning element. Cool. And now let's then zoom back a little bit and to have again the overview of our full battery pack as a whole. And here I want to maybe focus, we already see how the bill of materials here and maybe the structure, all of this we have already covered it, but I would like to focus on this small portion of this slide, that is the cost of the materials. because in an electric vehicle, the battery pack distribution of the cost usually looks something like this. As you can see, 51% of the cost is going to be related to the electrical components, and this includes the cells, the bus bars, the wiring harnesses, contactors, BMS, electronics, and so on. So it is an important part of our battery. But as you can see, 41% of it is actually mechanical components. So things, for instance, like the pack housing, the module frames, cooling systems, bolts, the seals, the tensioning system, all of this already has a big impact in the cost of the battery. And then we have 8% that goes to the cooling and heating components that are, for instance, the radiators, the pumps, the pipes, the sensors that we need to have over here. So you might be a little bit surprised that the mechanical part of the battery, things like the aluminum trays, the bolts, the gaskets, and so on, nearly cost half as much as the battery cell themselves. But this is because building a battery pack, it is not just about storing the energy, but it is about making sure that the pack can survive the car crash, that stays sealed against water, dust, and that dissipate heat properly, as well that fits into the vehicle platform without adding, for instance, unnecessary weight and so on. So with this, we conclude the overview of the product as well as the introduction. And now we can go through the production process. So we will look step by step, starting from raw materials and everything that you already visited in the previous sections or modules of this course, of how the batteries are assembled, all the way to the fully assembled and tested battery packs that are going to be ready to go into the vehicle. We will see how the batteries, how the modules are built, and how everything gets integrated safely and efficiently at a pack level. In the previous modules, you already studied how the lithium-ion batteries are actually produced. This diagram shows the entire production process, also recapitulating a little bit the production of the battery cells from the raw materials all the way to having the battery cell that is going to be the main component of our battery packs. However, we will focus on the last two phases that are the battery module assembly and the battery pack assembly. So this we will cover in deep in the next slides, a big overview. In the battery module assembly, what we will do is to group the cells into the modules, to add the electrical connections, to add the sensors, to assemble the module into the final pack with the cooling systems, with the enclosures, and to run the full system testing before actually shipping. So let's see how each of these steps and what are the tasks and the specific steps that we have to do in this process. And we start then with the pre-assembly. At this first point, we have already as the input, we have the finished cells, the cells that have gone through the whole assembly process, fabrication. They have gone through the formation, aging, and testing. And after that, we can then group them into the modules. And first, we have to prepare them properly, and that is what will happen here in the pre-assembly process. The first step then is the sorting of the battery cells. When the battery cells arrive into the production line, the first thing we do is to scan the product and to see that have a visual inspection of the product as well. We sort the cells based on their performance data, like for instance the voltage, the capacity, the internal resistance, and like this we can make sure that we will group cells that have similar performance together. This will help the entire module to last longer and to perform better. So if a cell doesn't meet the standard, then maybe because its capacity is too low or the resistance of the cell is too high, then it is sorted out because this can pose a problem to the module later in the future. So after we have sorted the battery cells, we also have this receiving inspection of them. In some cases, we can even have electrochemical impedance analysis, which tell us if the internal chemistry of the cells is healthy or not. And after that, we can then go through the surface cleaning process. Depending on how the cells are being chipped and also on how we are gonna assemble, we may need to clean the surface of these batteries, especially the electrodes and the electrical tabs of the battery. Sometimes there is dust, sometimes there is oxidation, sometimes there is oil residues that could make it harder to weld later. So we need to have this surface cleaning. Also, in some cases, we can have surface activation methods like plasma treatment, for instance, to improve the welding quality later on. After this step, we go to the next step, that is going to be actually joining the cells and to create the stack of the cells. So for prismatic or in the case of pouch cells, we can apply glue, either liquid glue or solid tapes, and this will be the joining medium that also creates electrical insulation between the cells because we don't want to have short circuits between cells. Once we have applied the glue, the next step is then to stack them. The cells are going to be stacked in the defined way, depending on the architecture and the array of the modules, according to the mechanical distribution, in order to prepare them to later have the electrical connections. There are some automatic or robotic arms that can handle this task with a very high precision, as you can see here, for instance. Now that the cells have been already stacked and they have been pre-assembled, the next step is to insulate and to put the tension elements around the stack properly. This is going to be critical because it's going to be part of the module production, and it is the part that will ensure the safety, the thermal control, the mechanical stability during the battery lifetime. So it is very important. We start then pressing the stack, applying some pressure with a pressing device, and this is going to be applied. This device is going to apply a defined pressure into the whole stack of the cells. This pressure helps to minimize the gaps between the cells and to create a clean and solid block that we can then go through the next steps. After that, we can include some insulation plates, as you can see over here. We place plastic plates or special foils between the cells and also around the stack. This will allow us to have electrical insulation, so we ensure that there is not current flowing accidentally between the cells or between the modules. And also, in some cases, it provides thermal management because it allows us to avoid thermal runaway and to interrupt the chain of reactions and to slow down the transfer of heat between cells. That is also very important. Then the next step is to position and to secure all the components together. Depending on the design, we may use glue or screws to fix the stack inside of the module housing, as you can see over here. And especially with, for instance, pouch cells, we need to have some drawer system or a way to slide the battery cells inside of the frame and to keep everything clamped afterwards. And in these last parts, we also include the tensioning. So once everything is in place, we tension the stack using the different methods that were presented in the slides before. Now that our cell stack is also insulated and it is tightly in place, we go to one of the most important and critical processes in the assembly of the battery, that is actually to create the electrical connections between the cells. So this is called the electric contacting, and as I mentioned, is one of the most critical steps in the module assembly process, because we need a lot of precision and it has to happen in a very safe manner. In this process, basically, each of the battery cells will be connected to the contact tabs or the bus bars that are going to be used to carry the current. We use those tabs to wire the cells together, either in series or in parallel, or in a combination of both, depending on the design of our battery module. These connections are typically made using the metal bus bars or welding strips or nickel tabs, for instance. There are going to be several methods to join and to create these connections. Here are 4 of the most common ones. First, we have, for instance, the ultrasonic. This is a method that uses high frequency vibrations to weld the metal parts together. It is, on the good side, it is very fast and does not produce heat, so it's very gentle with the battery cells. However, it is very expensive itself. And the other method that we have is, for instance, the laser welding that is shown here. This is way much precise. In this case, we use a focus laser beam to melt and to join the metal. It is going to be great to be used in automated lines and in very complex layouts, because even if it is more expensive, it has very good tolerances and it is very precise. On one of the sides that we have on this method is that it creates more heat than the ultrasonic methods, and because of that it has to be done carefully. Another method is, for instance, the current welding or spot welding. In this case, we use current pulses to heat up the metals and to melt them together. It is one of the cheapest methods because it requires very low investment. However, it is very dependent to the materials that we are going to be trying to weld together, and also generates a lot of heat, so it is not so gentle with the battery cells. And the last one is to use screws or bolts as connection methods. This method is used when we want to have some when we want, for instance, to disassemble the battery modules and the packs. However, it is not very recommended because the electrical resistance at the joint is not going to be the lowest. Once we have completed this connection, usually we have a last stage, that is to measure and to test that the connection has a very low resistance across the joint, that it has the mechanical strength that it's supposed to have, and also to have a visual inspection of it, even in some cases with X-ray scans, to check the quality of the welding points in the automated lines, but also in the manual lines. Then the next step is to include in our batteries the monitoring and control systems. That is going to be critical. In this case, we are going to mount the BMS slave, all the small circuit board that goes into each of the modules that are going to be placed. Also the temperature sensors as well as the voltage sensors. All of these elements are going to be mounted in place. Once we have that, we will also connect the plugins, test the assembly, and to validate that the system runs according to the specifications. Basically, we connect all of our sensors to the BMS board, the local BMS board, and we check that the signals, the voltages and the temperatures are being reported correctly. In the next step, we close the module up, literally. So we run some final tests to make sure that everything is safe and is working properly. And then we attach the cables and the connectors before we close the lip. We can make sure that all the cables are in place correctly, that we have the power cables that are handling the high voltage, but also the communication cables that are going to be taking the data exchange between the modules and the main BMS are in place, and they are routed inside different channels and holders to avoid damage because of vibration and rubbing and so on. We also connect here any controller and cooling system if it is needed, and at the end we place the lid of our module. Either we screw on or we snap into place depending on the design, and we close mechanically the module, and finally we run some tests at the module level. Usually this will include the visual inspection. We check the module voltage, we check that the module is balanced and that the cooling system is working properly. Now we have officially completed the module level work, and we can step into the next stage, that is to actually assemble the full battery pack. And this is where the things really start coming together. The module with the rest of the components integrate the full battery pack. So the first step after completing the module is gonna be to have the module's insertion into the pack. We can think of this like packing the suitcase. That is the analogy that we are having for the pack. And here we are placing very precise the high voltage energy blocks into the carefully designed tray that we see over here. The first step in some cases is the installation of the cooling plates that are shown here. At the bottom of the pack housing, we usually install the cooling plates first, and they are often made of aluminum, or they contain the challenge for the liquid coolant to flow around. After we have that, then we can go to the module insertion and to place each of these modules in their intended location. For this we can use robotic grippers, or we can also have manual lifting tools depending on the setup of our factory. Here is very important to have precision, since each module must be placed in the exactly right location to line up with the connectors, with the coolant fittings and so on. Once we have that, we have to repeat it until all of our modules are placed. In this diagram here, we see that at the end we have the 3 models in this pack inserted, but a real pack can have already dozens of these models. Then the next step is gonna be to secure everything firmly and to screw our cells modules in place. So this is all about fixing the modules in the position they are intended to be, so they don't move around due to the vibrations, the shocks, and the thermal expansions during the vehicle life. We have different mechanical fixations, and all of this is pre-designed based on the different mounting points in our tray pack and in our modules. We can also include at some point here vibration and crash protections. As you know, EVs are exposed to constant vibrations, especially when we are driving on rough roads or in long distances. So if the modules are not tightly secured, they can move slightly, and over time this can damage the electrical connections and also to end up wearing down the insulation. So here we have to include some protections to avoid that. And finally, we have also some design details that come into place to fix everything together. Now that the modules are already in place and are firmly secure, we can move to one of the most complex and important stages in the battery pack assembly, that is going to be the electrical and the thermal integration. So this is the step where we connect everything together. We will connect the power lines, the data line, the cooling sensors, the control units, so the pack can work as a unified system and not only as independent components. The order of this process will depend on the battery itself, but we can start, for instance, with the cooling system integration. So we install and connect the cooling system. Usually, if it is a liquid cooling loop, we already do all the mechanical connections, and we ensure that the pumps, the valve, the temperature sensor, all of it is wired and sealed correctly. Then the next step is to connect the high voltage system and wires. This includes connecting the relays, the contactors, the fuses, the pre-charge resistors if it is included there, and sometimes current sensors, insulating monitoring devices, and for instance the high voltage disconnect switch if it is requested. And the last step is then to connect the low voltage wiring and to connect the battery management system, the master of it. So to collect the signal from all of the modules and to wire them to the master BMS. The power lines are also connected, as well as we validate that the BMS is working correctly, that is collecting the data from all of the modules and that is communicating with the vehicle appropriately. And yep, finally, the connection from the battery to the vehicle. We test that the interface is placed correctly in the position that it meant to be, and that is also wired to the BMS. Then at this point we already have everything connected, power, data, cooling, and we are very close to seal our battery. So in this last step is how we assemble the cover of the battery pack. This has to be airtight, it has to be safe, it has to be sealed from the outside world. So what we do in this last step is to apply the seal. We can use, for instance, rubber gaskets or spray foam, or to glue the seal with adhesive, and to use different techniques to keep out the moisture, the dirt, and the dust. Also, we need to ensure that the coolant and the gas is completely sealed and we are not having leakages of all of any of these components before closing the battery. Then, when we are sure of it, we mount the cover. We place the upper part of the housing or the lid of it, and then we screw it into place, and we use different screws, as you can see here. in the perimeter of the battery to keep it together using a specific torque and specific tools to make sure that the pressure in the battery and the pressure is the designed one. And after doing that, the next step is actually to bring the battery to life. So what we are gonna do is to perform an initial charge of our battery and to also load the software that is gonna be running in the first functional test. So the first step is to flash the BMS software. We connect the battery pack to the diagnostic computer. We flash the battery management system. Basically, we install the operating software that it will be running, and we take all the measurements and report of the variables that the BMS is going to be sending. We do the initial charging and we validate that everything is working as expected. Also, in some cases we can put a thermal camera to inspect that the thermal management system also is working. We validate that we don't have any hotspots, that we don't have any bad welds or loose connections that are going to be creating undesirable high resistance and that are going to be generating heat in our battery pack. And after doing that, we have come to the end. So there is the final production step, that is the end of the line testing. This is the very last checkpoint that we have with the battery pack. In this case, we will label the battery that is ready and that is approved to be shipped to the car factory. So the end of the line testing is like the final mechanical exam and medical exam that we have of our battery, where we will be checking that everything inside of the pack is healthy, is functional, and it is safe. In this case, we use testing equipment and we hook it to the battery to do a specialized test station to validate the high voltage connectors, to validate the low voltage communications, and to ensure that everything is working correctly and that the battery is ready to be shipped. We can include here, for instance, charge and discharge testing, including visual inspections for it, as well as the labeling and the final approval of the battery. So with this, we have reached out the end of today's session for our battery module and pack production. I hope that you have so far and that you have learned a little bit what is the process of battery pack assembly and battery module assembly. We have started this session by understanding the basic building blocks of the modules, the packs, all the supporting components, and we have analyzed the different functions that they have. Also, we look at how different cell types, cylindrical, pouch, prismatic, will affect the module design and the manufacturing of it. And finally, we have walked through all the production process and also see precisely how every step is needed to have a clean assembly, good insulation, solid welds, robust sealing in the battery, and also to ensure that our battery is completely tested. So we have go to the end. The final gate is to ensure that each battery pack is safe, functional, and ready to be used in the world applications. Thank you for your attention and see you in the next session.